Somewhere within this extraordinary image are countless planets that humanity has never discovered. Not just a handful, but perhaps hundreds or even thousands of hidden worlds scattered among more than 60 million stars packed into the crowded heart of the Milky Way. At first glance, the image looks like a breathtaking work of art, but for astronomers it is something far more valuable. It is a cosmic map waiting to reveal invisible planets through the subtle effects of gravity. The scene is almost overwhelming. Stars are packed so closely together that the glowing center of our galaxy appears more like a river of fire than a collection of individual suns. Clouds of glowing gas weave through thick lanes of dust while distant star clusters fade into the background. The stellar density is so extreme that even sophisticated image processing software initially struggled to separate one object from another. Yet this observation is far more than a spectacular photograph. It represents a reference image that future astronomers will compare against as hidden planets briefly reveal themselves through gravitational microlensing. Deep within the galactic bulge, stars constantly move across one another from our point of view. Occasionally, a foreground star aligns almost perfectly with a much more distant background star. When this rare alignment occurs, gravity bends and magnifies the distant starlight like a natural cosmic lens. If the foreground star hosts a planet, that planet produces a tiny additional distortion in the light. It never appears directly in the image, yet its gravity leaves behind a brief signature that scientists can detect. In this way, an invisible world quietly announces its existence without ever being seen. Euclid has not simply photographed the center of our galaxy. It has created the foundation for discovering worlds that remain completely hidden from ordinary observation. Although Euclid was designed primarily to investigate the dark universe, this remarkable observation focused on one of the brightest and most crowded regions of the sky. Its primary mission is to map billions of distant galaxies and help scientists understand dark matter, dark energy, and the large-scale structure of the cosmos. Normally, the telescope observes relatively empty regions where faint galaxies can be measured without interference from nearby stars. This time, however, it deliberately turned toward the densely populated galactic bulge, where millions of stars are compressed into a relatively small region of space. Observing such an area is extremely challenging. The intense brightness and enormous concentration of stars can overwhelm instruments built for precision measurements. Ironically, those same conditions make the region one of the best places in the galaxy to search for planets through gravitational microlensing. This technique depends entirely on chance. A foreground star must drift almost perfectly in front of a background star. As gravity bends the light, the distant star gradually brightens before fading back to normal. If a planet accompanies the foreground star, it briefly creates a small disturbance in the smooth light curve, revealing its presence through gravity alone. These alignments are exceptionally rare across most of the sky. Near the center of the Milky Way, however, millions of stars overlap along our line of sight, dramatically increasing the likelihood of these events. That makes this region one of the richest hunting grounds for hidden exoplanets ever observed. Euclid's image therefore serves as much more than a beautiful portrait of our galaxy. It provides an extraordinarily detailed snapshot containing over 60 million stars whose positions, brightness, and motion can be measured with remarkable precision. As future observations monitor this same region, astronomers will compare every tiny change against this baseline, searching for the subtle fingerprints of unseen planets. Most people are familiar with the transit method of discovering exoplanets. When a planet crosses directly in front of its host star, the star's brightness decreases slightly. Repeated observations allow scientists to estimate the planet's size and orbit. Microlensing works in an entirely different way. Instead of watching a planet block starlight, astronomers watch gravity reshape it. As a foreground star passes in front of a distant one, space itself bends the background light, temporarily making the distant star appear brighter. If a planet is orbiting the foreground star, its gravity adds a tiny extra signal that briefly interrupts the otherwise smooth brightening. This technique is especially valuable because it can detect planets that other methods often miss. It is capable of finding cold worlds orbiting far from their stars, planets too faint to observe directly, and even planetary systems buried within the crowded center of the Milky Way. Unlike transit searches, microlensing does not require planets to repeatedly cross their stars from our viewpoint. Instead, it relies entirely on gravity, allowing astronomers to discover worlds that remain invisible by every other technique.